Welcome, dear listener. Tonight, instead of scrolling past the stars, let's actually follow them. From the first humans who used the sunrise as a calendar, to Babylonian sky records pressed into clay, to telescopes that turned planets into worlds, to modern observatories that watch the universe change in real time, this is the full story of how we learned to read the night. If this cozy story helps you drift off, please subscribe, tap like, and leave a gentle comment. Your support keeps the journey continues. Tonight you can lift your phone and the sky will politely label itself for you. Jupiter, Mars, Saturn, as if the universe is wearing little name tags and has agreed to be helpful. Then you lower the phone and the labels vanish, and you are left with what our ancestors had for most of human history. Darkness, stars, and a quiet feeling that time is moving whether you notice it or not. Astronomy begins as noticing. It begins with someone realizing that the sun does not rise in the same place every morning, and that this small sideways drift along the horizon is the difference between planting too early and planting too late. It begins with a shadow from a stick, a gnomon, stretching and shrinking across packed earth. It begins with breath in cool dawn air, a wool cloak pulled tighter, and the patience to look again tomorrow. Before writing, the sky is remembered in bodies and landscapes. People return to the same ridge, the same gap between stones, the same doorway that frames the sunrise at a turning point of the year. In many places, builders set stones and passages so that a solstice sunrise or sunset arrives like a visitor who knows the address. These monuments are not telescopes and they are not laboratories, but they are communal memory made solid. They say without speaking that the year has joints and hinges, and that the sky can be used as a calendar if you build your life around it. The moon offers a second rhythm closer and more intimate. A crescent becomes a bowl, becomes a bright coin, then thins to a delicate sliver again. Lunar months are easy to count, and many early calendars begin there. The problem is that the moon and the seasons do not line up neatly. 12 lunar months are a little too short for a solar year, and 13 feels like cheating unless everyone agrees to it. To keep them together, communities add extra days or an extra month now and then, a quiet negotiation between arithmetic and moonlight and the solar year. Early skywatchers learn a truth that will haunt calendars forever. Nature does not always fit into neat human boxes. Some archaeologists have suggested that very old notched bones and tally marks may reflect lunar counting, though interpretation can be uncertain. What is not uncertain is the larger pattern. Across cultures, people build systems that link the sky to food, travel, ritual, and authority. The heavens become the oldest shared clock face, and the first great innovation is simply consistency. In Mesopotamia, on the wide plains between the Tigris and Euphrates, consistency becomes an art. Scribes press wedge-shaped marks into clay tablets that cool in the hand. Night after night, observers record the first visibility of the lunar crescent, the dates of eclipses, the wanderings of bright planets against the fixed stars. These records are practical and also symbolic. The sky is read for meaning, and it is also read for timing. When you live with rivers that flood and fields that must be managed, prediction feels like a form of safety. Over generations, Mesopotamian astronomers learned to recognize cycles. Eclipses return in patterns that can be anticipated, and the Saros cycle becomes one of the tools for forecasting them. Star lists are compiled. Constellations are named. The ecliptic, the path along which the sun and planets travel, becomes a kind of celestial roadway with recognizable milestones. Eventually, the zodiac appears as the division of this path into 12 segments, a scheme that makes the sky easier to compute and share. If you have ever tried to organize a messy closet by adding labeled boxes, you understand the emotional appeal. The key point is not the later horoscope tradition, which grows in many directions. The key point is the mathematical habit. The heavens can be reduced to patterns, patterns can be turned into numbers, and numbers can be used to predict what the sky will do next. This is a profound shift. The sky stops being only a story told by elders and becomes something you can test against next month's sky. In Egypt, the sky is also a keeper of order, but with a different flavour. The Nile's rhythm shapes life, and timekeeping becomes a civic necessity. Star groups called decans rise one after another during the night, and their sequence helps mark the hours. Temples and administrations use calendars to coordinate labour, ritual, and taxation, and the stars become part of the machinery of the state. You can imagine an official counting nights by starlight, trying to look serious while secretly wishing the cosmos offered a quicker checkout line. Egyptian timekeeping is often solar in its civil form, with a year organised into months and days to keep administration running, even as the true seasonal year slips slightly. Here again you see the theme: people build a calendar that is good enough to run a society, then spend generations adjusting, compensating, and arguing about it. The sky is steady, but human schedules have feelings. Across East Asia, long traditions of observation develop with remarkable continuity. In China, court astronomers record eclipses, comets, and the sudden appearance of new stars, the so-called guest stars. These notes are often tied to the responsibilities of governance, because the sky is treated as a mirror of earthly affairs, but the observational habit has an additional legacy. Centuries later, such records help modern astronomers identify supernovae and other transient events, because someone long ago looked up and wrote, in careful strokes, that the night changed. The observational work is not always glamorous. It is repetitive, often cold, and sometimes inconveniently timed. The sky has a talent for staging an eclipse at the exact moment you would prefer to be inside near a hearth. But careful record-keeping is itself an innovation. It turns astronomy into a cumulative practice. One generation does not have to start from scratch. A new observer can inherit a notebook that is already centuries deep. In the Indian subcontinent, astronomy grows alongside mathematics and the deep need to reconcile lunar months with solar seasons. Early traditions focus on calendrical structure and computational methods, refining parameters so that predictions match what is seen. This is astronomy as craftsmanship. If a model drifts, you adjust it. If the moon arrives early, you account for it. The goal is a calendar that keeps faith with the sky. And the sky, famously, is not sentimental about human plans. Now we drift toward the Greek-speaking world, where a particular change takes place. The sky is not only recorded, it is explained with geometry. Think of a quiet room with an oil lamp, a wax tablet, and a mind that loves shapes. Greek philosophers and astronomers argue that the Earth is a sphere, using observations like the curved shadow on the moon during eclipses and the changing height of stars with latitude. They begin to treat the heavens as a system that can be modelled with circles and angles, as if the sky is a grand diagram waiting to be drawn. Circles become a favoured tool because they feel perfect and repeatable. If you have ever tried to draw a circle freehand and then stared at the wobble in disappointment, you understand why an ideal circle becomes an object of devotion. The heavens, in this view, are orderly and should move in orderly ways. The philosophical preference shapes the models that follow. Instruments develop to help the eye and to discipline the imagination. Simple sighting tools and graduated circles let observers measure angles more precisely. Armillary spheres model the sky with rings, giving physical form to an abstract idea. The key innovation here is the marriage of observation to calculation. The sky is no longer only a story, it is also a coordinate system. Star cataloguing becomes a major milestone. To catalogue stars is to admit that the sky can be mapped and that the maps can be compared across time. Hipparchus, working in the 2nd century before the Common Era, is associated with careful stellar positions and with the recognition that the celestial background shifts slowly over long periods. This slow drift, later called precession, is subtle, the kind of change you might miss unless you are both meticulous and stubborn. It is the sky whispering that even the seemingly fixed stars are part of a larger motion. Hipparchus also refines methods for predicting eclipses and brings mathematical techniques to bear on astronomical problems. He helps turn celestial motions into something you can compute, not just watch. The heavens begin to resemble a well-tuned instrument, and humans begin to imagine themselves as its listeners, leaning close. By the time of Claudius Ptolemy in Alexandria, in the 2nd century of the Common Era, many strands of ancient astronomy are gathered into a grand synthesis. Ptolemy compiles observations and star positions and, most famously, presents a mathematical system that predicts planetary motions seen from Earth. In this system, planets move on circles whose centres move on other circles, a nested geometry of epicycles and interference. It is not a description of physical causes in the modern sense. It is a powerful machine for prediction, and prediction matters. In the ancient world, the difference between a sky that surprises you and a sky that can be anticipated is enormous. Navigation, agriculture, ritual calendars, and the sheer human desire to make tomorrow feel less mysterious all lean on astronomy. The ancient astronomer is often a timekeeper, a calculator, a librarian of the heavens. Their tools are patient eyes, steady hands, and tables of numbers that must be copied without a single smudge, because one mistaken digit can send a forecast wandering like a lost goat. There is something oddly comforting about this stage of astronomy. The universe is imagined as orderly, layered, and intelligible. The planets wander, yes, but they wander according to rules you can write down. The sky becomes a book that can be copied, a table that can be consulted, a tradition that can be taught. And that tradition will travel far, translated and recalculated, cherished and challenged, because it works well enough to keep ships on course and calendars on track. So let this first part end quietly. Picture a lamp burning low, a reed pen scratching, clay cooling, parchment absorbing ink. Outside, the night sky turns with the same calm it always had. You do not need a phone to know it is there. You only need the ancient human habit of looking up and the simple shadow of a stick on the ground, marking time one patient line at a time. When you think of astronomy advancing, it is tempting to picture a lone genius under a starry sky, dramatically discovering something while the universe politely applauds. In reality, for long stretches of history, the heroes are quieter. They are translators with tired eyes, instrument makers with metal filings on their sleeves, and observers who do the same careful thing thousands of times until the sky starts to give up its secrets. After the ancient world builds its first great predictive models, the story of astronomy becomes for a while the story of travel. Not travel by ship alone, though there is plenty of that. Travel by manuscript. Travel by memory. Travel by a line of text copied in lamplight, carried across deserts and seas, then copied again and again, until it arrives somewhere new with a few extra notes in the margin. You can imagine a book as a kind of bottled starlight. It holds a night sky from another century, but books are fragile, and so the continuity of astronomy depends on communities that value preserving and improving what they inherit. In late antiquity and the early medieval period, astronomical knowledge passes through many hands and languages. Greek works are studied, summarized, challenged, and translated. Tables of planetary motion are recalculated for new longitudes. Star names and constellation lore shift as they cross borders. The sky stays the same, but the way people describe it becomes wonderfully multilingual, like the heavens have joined an international conference. In the Islamic world, from the 8th century onward, astronomy becomes both a practical science and a prestigious one. Cities support scholars who want accurate calendars, reliable prayer times, and correct directions for sacred geography. Navigation and timekeeping demand better techniques, and courtly culture often supports the building of libraries and observatories. This is not astronomy as a hobby, it is astronomy as infrastructure. Picture a workshop bench, warm from the day's sun, with brass discs and rulers laid out like edible pastries you're not allowed to touch. An astrolabe takes shape there, a compact sky you can hold in your palm. Its engraved lines and rotating plates turn the heavens into a portable problem you can solve with your fingers. Instruments like these do not replace observation, they sharpen it. They teach the eye what to look for, and they teach the mind how to turn sight into number. Alongside instruments, mathematics grows as an essential companion. Astronomers refine methods for dealing with the sphere of the sky, because the heavens refuse to flatten themselves into a neat page. Trigonometry becomes a trusted tool not as an abstract exercise, but as a way to keep calculations aligned with reality. The goal is simple to state and hard to achieve: predict where the sun, moon, and planets will be, and do it accurately enough that the world can run on it. This is also a period of serious critique. Scholars read older models with respect and with a willingness to question them. They compare predictions against observations, and when the predictions drift, they adjust parameters and sometimes invent new geometric techniques to repair the mismatch. There is a practical honesty in this. You do not win points for loyalty to a theory if the moon refuses to show up where your table says it should be. A Across the centuries, observatories become more than a metaphor. They become institutions. Some are modest, some grand, but all depend on the same ingredients: stable instruments, trained observers, clear procedures, and records that can be checked. In places like Moraga and later Samarkand, astronomers build large-scale tools that trade portability for precision. A giant quadrant or sextant built into stone can measure angles with an authority that a handheld instrument cannot. It is like the difference between a pocket ruler and a carpenter's bench that does not wobble. Ulugh Beg's observatory in Samarkand is a particularly vivid example of this impulse towards scale and precision. You can picture the sweep of stone, the careful carving of graduated markings, the cold air at dawn, and the sense that the building itself is a measuring device pointed at the sky. The output of such work often appears as zijez, astronomical tables and handbooks that condense years of observation and calculation into usable form. They are the spreadsheets of their day, only with fewer menus and more ink stains. While these developments unfold, other regions maintain their own deep astronomical traditions. In China, official astronomers continue meticulous recording of eclipses, comets, and unexpected celestial events, and calendars are repeatedly reformed to keep them aligned with seasonal reality. The craft of observation remains closely tied to the state, because timekeeping is power, and a reliable calendar is a form of social stability. In the Indian subcontinent, astronomical calculation and calendrical refinement continue in parallel, shaped by the ongoing challenge of reconciling lunar and solar cycles, and by the rich mathematical culture that supports such work. Across Eurasia, the sky is the same, and yet the methods for taming it are varied, inventive, and deeply human. Then, gradually, the story begins to pivot toward Europe in the later medieval period. Not because Europe is uniquely curious, but because a set of historical pressures converge. There is growing maritime navigation, expanding trade, and a hunger for standardized texts in universities and courts. Crucially, there are translation movements that bring astronomical works into Latin, and later into vernacular languages. Centres such as Toledo become bridges where Arabic texts and commentaries are translated, studied, and absorbed. Astronomy is once again on the move, and it carries with it both the inherited ancient framework and the improvements made over centuries of careful work. In European ports, sailors want practical answers. Where am I on the sea? What time is it? How do I keep a course when the shoreline has disappeared? Instruments like the mariner's astrolabe and crossstaff appear as rugged cousins of scholarly tools designed to survive wind, salt, and the unromantic reality of being dropped. The sky becomes a navigational partner, and the demand for accurate tables becomes urgent. Ephemerides and almanacs become valuable commodities. If you can predict the sky, you can help people cross the world. And then printing arrives, and it is difficult to overstate what this does. A table copied by hand is an invitation to error. A table printed and distributed widely becomes a shared reference point, and it spreads techniques faster than any caravan. Astronomy benefits enormously from this. When many people use the same tables, mistakes are noticed. When many people read the same arguments, debates sharpen. Knowledge gains a kind of mass, and mass creates momentum. By the 15th and 16th centuries, the old geocentric models still dominate learned astronomy, largely because they work well enough for prediction. But cracks are visible, planetary motions are complex, predictions need constant patching, and there is a growing sense that the system is a machine made of clever adjustments rather than a window into how the cosmos truly operates. Into this tension steps Copernicus. He proposes a sun-centered arrangement in which Earth is also a planet in motion. This is not an immediate overthrow of the old order. It is a reorganization that trades one set of complications for another. It still uses circular motions and still requires careful mathematical work. But it offers a striking conceptual simplification. Retrograde motion, the odd looping of planets against the stars, becomes an effect of Earth's own movement. The sky looks strange because we are moving too. It is a quietly radical idea, like realizing the train station is not drifting, your train is. Copernicus's model does not instantly win because it is elegant. Astronomy is not a beauty contest, though it occasionally pretends to be. The question is accuracy, and the question is evidence. To answer those, you need better observations than most people have. That need is fulfilled with extraordinary stubbornness by Tycho Brahe. Tycho builds an observatory culture before telescopes, and that is the miracle. He constructs large instruments, trains assistants, and measures planetary positions with an accuracy that makes older datasets look soft around the edges. He treats measurement like a craft worthy of a lifetime. You can almost hear the scrape of wood, the clink of metal fittings, the turning of screws by lantern light. Tycho's sky is not a poetic ceiling, it is a target. Tycho also lives through celestial events that challenge old assumptions. A new star appears in 1572, and later a great comet passes through the heavens. Observations suggest that these phenomena do not behave like nearby atmospheric tricks. They seem truly celestial, undermining the notion of an unchanging, perfectly layered heaven made of rigid spheres. The heavens, it turns out, can surprise you. Even after centuries of record-keeping, the universe keeps a few cards in its sleeve. Tycho himself does not fully embrace the Copernican arrangement. He proposes a hybrid system, trying to preserve certain philosophical and observational preferences while accommodating the mounting evidence that the old picture is strained. This is an important lesson in how science often moves. People do not jump from one worldview to another in a single dramatic leap. They build bridges, they compromise, they keep working. The real transformation arrives with Johannes Kepler, who inherits Tycho's precious trove of data and brings to it a relentless mathematical imagination. Kepler wants the model to match the sky, not the other way around. When circular orbits refuse to fit the observations, he does something psychologically difficult. He lets the circle go. Planets, Kepler finds, move in ellipses with the sun at a focus. Their speed changes with their distance, sweeping out equal areas in equal times. These are not merely computational tricks, they are regularities in nature. The heavens begin to look less like a set of perfect divine gears, and more like a dynamic system with rules that can be discovered. Kepler's work is a triumph of patience and humility. He spends years wrestling with numbers, returning again and again to the same stubborn discrepancies until a new pattern emerges. If you have ever stared at a problem too long and then, at last, the solution arrives not with fireworks but with a tired sigh of relief, you understand the feeling. Kepler's laws make prediction more accurate and the underlying picture more coherent. The universe begins to feel physically legible. By the time Kepler produces tables based on his new laws, astronomy stands at a threshold. The sky has been watched for millennia, recorded on clay and bamboo and parchment. Instruments have evolved from shadows and sighting sticks into engraved brass and monumental stone. Models have shifted from myths of meaning into mathematics of motion. And now, thanks to the marriage of precision data and daring theory, the planets move in a way that can be described with startling clarity. Yet the eye is still the eye. The observer still squints into darkness, still fights haze and fatigue, still measures what can be measured with naked sight and careful geometry. The next leap will come when glass enters the story and the sky stops being only a map of points and becomes a landscape of detail. For now, let this part end with a quiet image. A brass instrument rests on a wooden table. Its scale is finely engraved, each mark a promise of accuracy. Somewhere nearby, a page of numbers dries in ink. Outside, the stars turn slowly, indifferent and dependable. And the human mind, holding its breath, is already reaching for a new way to see. If you have ever looked through a smudged window and thought with mild annoyance that the world could be sharper, you already understand the emotional engine of Part 3. Astronomy has spent thousands of years training the human eye to be patient and precise. Then, in the early 17th century, someone points a tube of glass at the night sky and the universe becomes inconveniently detailed. The telescope does not arrive like a royal decree. It arrives like many useful things do, as a practical curiosity that turns out to be revolutionary. Lenses had been used for magnifying and for spectacles long before they were aimed at the heavens, but once the idea spreads that glass can bring distant things closer, the sky is the obvious next target. A bright planet is already calling attention to itself. The moon is already teasing the mind with patterns. You can almost feel the moment when a maker, a tinkerer, A person with an orderly bench and a messier imagination thinks, what happens if I point it up? When Galileo Galilei turns a telescope toward the moon, the old idea of a perfectly smooth, flawless heaven starts to lose its footing. The moon shows shadows that behave like shadows on mountains. Light falls on ridges and leaves craters dim. The lunar surface looks like a place, not a polished symbol. This is not just a new picture. It is a new category of reality. The sky has texture. Then the telescope begins to hand out surprises, as if it's enjoying itself. Jupiter is no longer a bright wandering dot. It has small companions that circle it night after night in a way that looks unmistakably like a miniature system. Venus goes through phases, swelling and thinning in a pattern that fits neatly with a sun-centered arrangement. The sun itself reveals spots and blemishes, features that move and change, quietly undermining the notion that the heavens must be perfectly unchanging. The old cosmology has not yet vanished, but it is now forced to share the room with fresh evidence, and evidence is a difficult houseguest to ignore. This telescopic era is not only about discovery, it is also about refinement. Telescopes improve, lenses become better crafted. Astronomers learn to trust what they see, while also learning to doubt the ways glass can lie. They notice distortions, they develop techniques. The act of observing becomes more disciplined, less like casual stargazing, and more like a craft with rules. A steady mount matters, a measured scale matters. Even the simple choice of when to observe becomes part of the method, because the sky is clearer on some nights and mischievous on others. And then comes a second transformation, quieter at first, but just as profound. The sky is no longer only something to look at, it becomes something to explain with physical laws. Isaac Newton enters this story like a person who has found a master key, and is both pleased and slightly alarmed that it opens so many doors. Building on earlier work in motion, and on Kepler's laws of planetary movement, Newton develops a framework in which the same rules govern an apple falling and the moon circling Earth. Gravity is not a local habit of our planet. It is a universal relationship. Suddenly the heavens are not a separate realm made of special stuff. They are part of the same world, running on the same logic, only with better lighting. Newton also changes the telescope itself. Refracting telescopes, which use lenses, struggle with colour fringes, because different colours of light bend by different amounts. This chromatic problem means bright objects can look haloed, as if the universe has taken up watercolour painting. Newton's reflecting telescope uses a mirror instead, and mirrors do not split light the same way. The design is compact and powerful, and it becomes a foundation for many of the large telescopes that follow. It is a lovely irony that the instrument for seeing farther depends on a perfectly shaped surface that must be polished until it behaves like liquid metal frozen in place. As the 17th century closes and the 18th begins, astronomy starts to look like a profession with a toolkit. Observatories grow in number and ambition. Clocks improve, because timing is everything when you measure the sky. The micrometer appears in the eyepiece, allowing observers to measure tiny separations between stars and planetary features. Star catalogues expand and become more precise. The sky turns into a grid that can be mapped with increasing confidence, and the maps begin to reveal a truth that is both thrilling and humbling. The universe is bigger than anyone thought, and it does not care if you feel emotionally ready. In this period, William Herschel becomes a kind of emblem of astronomical expansion. Herschel is a builder and an observer, someone who makes larger and larger telescopes and then uses them to sweep the sky systematically. He discovers a new planet, Uranus, not by waiting for a miracle, but by combing the heavens with the steady persistence of someone searching for a lost button on a dark carpet. He studies star clusters and nebulae, and he begins to imagine the Milky Way as a structured system rather than a simple band of light. His work suggests a galaxy with shape and depth, and his surveys make the sky feel less like a dome and more like a vast neighbourhood with districts you can explore. Telescopes keep growing, sometimes to heroic proportions. Large reflectors are built with mirrors of metal and later glass, and these instruments are not easy companions. They need careful alignment. They demand maintenance. They respond to temperature and gravity and human error with a stubbornness that feels at times personal. yet the payoff is enormous. Fainter objects appear. More stars fill the field of view until the old phrase fixed stars begins to sound like wishful thinking. One of the most important questions of this era is distance. Stars look like points no matter how large your telescope, which is a rude trick of physics. But if Earth moves around the Sun, then nearby stars should shift slightly against the background over the course of a year. This tiny shift is stellar parallax, and for centuries it remains frustratingly elusive. The absence of measurable parallax had once been used to argue against Earth's motion. The truth, however, is simpler and grander. The stars are so far away that the shift is minuscule. When astronomers finally measure stellar parallax convincingly in the 19th century, it is a milestone that feels like stepping from a shoreline onto open sea. Distances to stars become numbers rather than poetry. A star is no longer just bright or dim. It has a place in three-dimensional space. The sky deepens. During this same long century, astronomy undergoes a change in identity. It stops being only about positions and motions and becomes about the nature of celestial objects. This shift is powered by a deceptively simple idea. Light carries information. A prism spreads white light into colours, which is charming enough on a sunny wall. But when astronomers and physicists examine sunlight and starlight carefully, they see dark lines slicing the spectrum. These spectral lines are not artistic flourishes, they are signatures. Different elements absorb and emit light at specific wavelengths, and those patterns act like barcodes. It becomes possible to identify the chemistry of the Sun and stars from Earth without ever touching them. This is one of the strangest and most beautiful achievements in science, like learning the ingredients of a soup just by smelling the steam from across the room. Spectroscopy transforms astronomy into astrophysics. Stars are no longer anonymous points. They are physical objects with temperatures, compositions, and behaviours. Astronomers begin classifying stellar spectra, noticing regularities, and building a sense of stellar diversity. Some stars show strong hydrogen lines. Others show different patterns. The sky becomes not only a map, but a library, each star a volume with its own contents. At the same time, photography arrives and changes the relationship between the eye and the sky. The human eye is wonderful, but it is also impatient. It cannot hold a faint scene for long. A photographic plate, however, can collect light quietly over minutes and hours, stacking photons like careful coins. Details emerge that no observer could sketch accurately at the eyepiece. The sky becomes an archive you can store, revisit, and share. A single plate can be studied by many minds, and arguments can be settled with a kind of democratic evidence. The stars, in their silent way, begin to leave receipts. Photographic surveys expand the reach of astronomy. Nebulae are captured in intricate filaments. Starfields become dense forests of points. New objects are discovered not by chance but by systematic comparison of plates taken at different times. The idea of time enters the sky in a new way. The heavens are not just rotating, they are changing subtly and sometimes dramatically. Variables brighten and fade, novae appear. Motion can be detected. The universe starts to look alive, though it remains very bad at replying to correspondence. As the 19th century draws toward its end, astronomy has become a layered enterprise. There is still positional astronomy, the careful measurement of where things are and how they move. There is celestial mechanics, the mathematics of gravity and orbits. There is observational technique, the craft of building and calibrating instruments. And now there is astrophysics, the study of what celestial objects are, made possible by spectroscopy and photography. Each layer adds a new kind of understanding, and together they make the universe feel both more knowable and more enormous. So we end this third part with a quiet scene that could belong to many observatories of the era. A dome turned with a low groan. A clock ticks with stern devotion. A telescope, heavy and patient, points into darkness. Somewhere in the building, a glass plate waits in its holder like a blank page. Starlight falls onto it, line by line, grain by grain, turning into a record that can outlast the night. The ancient mark that began as a notch and then became ink is now a trace in silver, and the sky, once a ceiling, is now a laboratory written in light. If part 3 is the moment the universe steps closer to the eyepiece, Part 4 is the moment the universe learns to speak in many voices at once. Light, radio, X-rays, ripples in space itself, all arriving like different instruments in the same orchestra. The modern sky is no longer something you only look at. It is something you listen to, measure, archive and share, often before your coffee is even cooled. At the start of the 20th century, astronomy already has powerful telescopes, spectroscopy and photography. It can map positions, classify starlight and capture faint nebulae on glass plates. But it still lacks a full physical explanation for the engines inside stars, and it still argues about the scale of the universe with the earnest intensity of people who have been awake too long. Then physics changes the lighting in the room. Relativity arrives and quietly rearranges gravity. Instead of a force reaching across space like an invisible hand, gravity becomes the shape of space and time themselves. The practical payoff for astronomy is enormous. Orbits, light bending, time running at different speeds, all become parts of one framework. The sky is no longer a clockwork of circles and corrections, it is a stage where the geometry of the universe matters. Around the same era, astronomers wrestle with a question that sounds quaint now but once felt like a cliff edge. Are the spiral nebulae inside our Milky Way? Or are they distant island universes on their own? The answer comes from careful, patient work with variable stars and distance measurements. When Edwin Hubble and others show that some of these objects are far beyond the Milky Way, the universe expands in a single conceptual step. The night sky stops being a local neighbourhood, it becomes a city of galaxies, and then it expands again. Galaxies appear to be moving away from one another, with distance tied to recession speed. The universe is not static, it is stretching. This is not merely a new fact, it is a new kind of story. If the universe is expanding now, then in the past it was smaller, denser, hotter. Cosmology turns from philosophy into a science with evidence, and the evidence is written in the red-shifted light of galaxies. Meanwhile, the question of what powers the stars shifts from mystery to mechanism. Over the first half of the century, astrophysicists developed models of stellar structure and evolution. The idea that stars shine by fusing lighter elements into heavier ones becomes central, tying starlight to nuclear physics. The sun becomes not a special lamp hung in the sky, but a self-regulated furnace of gravity and fusion. Suddenly the life story of a star can be told from birth in gas clouds to old age, and astronomy gains a new narrative backbone. The sky is full of objects that age. This is also the period when the universe begins to reveal itself beyond visible light. Radio astronomy starts almost accidentally, with the discovery that the sky emits radio static. After that it becomes irresistible. Radio dishes listen to the Milky Way's cold hydrogen, mapped through the famous 21 centimetre line, revealing the structure of spiral arms, and the hidden mass of gas between stars. The universe that looked empty to the eye turns out to be busy and murmuring. It is like realising the quietest person at the party is actually sending 1,000 messages. As technology improves, astronomers discover sources that are outrageously energetic. Quasars blaze from deep time, pulsars tick like cosmic lighthouses. Some galaxies broadcast powerful jets. These findings reshape the sense of what is possible in nature. The universe is not only serene, it can be violent in its own way, though from Earth it arrives as a distant discipline measurement on a chart. By the mid-20th century, the biggest cosmological debate concerns origins. Is the universe eternal and steady, or did it begin in a hot, dense state? One decisive clue comes in the form of a faint microwave glow filling the sky, the cosmic microwave background. This is the cooled afterheat of the early universe, a whisper from a time before stars. Measuring this background becomes a major project. Satellites and instruments map its tiny fluctuations, turning cosmology into precision work. The early universe leaves fingerprints, and we learn to read them. From the 1960s onward, astronomy keeps adding new senses. X-ray astronomy reveals black holes and neutron stars feeding on matter. Gamma-ray detectors catch brief flashes from across the universe. Infrared instruments see through dust to stellar nurseries. Ultraviolet observations trace hot young stars and energetic gas. Each wavelength is a different kind of truth. It is the same cosmos, but it changes costumes depending on how you look. Then comes spaceflight, which does something wonderfully simple. It lifts telescopes above the blur of Earth's atmosphere. Space observatories can see wavelengths blocked by air, and they can deliver sharp images without atmospheric shimmering. This transforms many areas of astronomy at once, from studying planets in our own solar system to mapping distant galaxies. The Hubble Space Telescope becomes a cultural icon not because it is the only telescope, but because it gives the public a clear, steady window, a reminder that the universe can be both real and breathtakingly photogenic. On the ground, detectors change too. The old photographic plate gives way to digital sensors, especially charge-coupled devices, that count photons with high efficiency and consistency. Astronomy becomes a science of data as much as a science of looking. The observer at an eyepiece is increasingly replaced by teams, pipelines, and careful calibration. A night of observing produces not a sketch, but a hard drive full of measurements that can be analysed for years. With better data comes a more complicated universe. Galaxies do not rotate the way they should if only visible matter exists, hinting at dark matter. The expansion of the universe appears to be accelerating, implying dark energy. These are not small adjustments. They are reminders that most of the universe is not directly visible. Astronomy, which began by naming the bright points, now spends much of its time investigating what cannot be seen directly, like a detective who's learned that the most important suspect is a shadow. In the 1990s and 2000s, another transformation arrives with a surprisingly emotional punch. Astronomers begin discovering planets around other stars in large numbers. What was once speculation becomes census. Worlds are found in strange configurations: close-orbiting giants, compact systems, planets around pulsars, planets in multi-star environments. The solar system turns out not to be the standard template. It is one example among many. As surveys improve, exoplanets become a field of atmospheres and chemistry, not just orbits. Astronomers chase the faint dimming of a star as a planet crosses in front, and from that dimming infer size, period, and sometimes the hint of an atmosphere. It is a delicate art. You're trying to detect a tiny shadow passing over a distant lamp, and you're doing it with the steadiness of someone threading a needle in a moving train. And the 21st century also revives one of the oldest dreams of astronomy: listening for changes, transients, asteroids, supernovae, variable stars, events that flare and fade become central. The universe is not a static map. It is a moving film. To study it well, you need constant coverage, fast alerts, and broad collaboration. This is where the modern astronomy community begins to resemble a global nervous system, passing signals quickly from one instrument to another. Then, in 2015, gravitational wave astronomy opens a new channel of perception. Instead of observing light, detectors measure tiny distortions in space and time caused by massive objects accelerating, such as merging black holes or neutron stars. It is as if the universe has been humming in a register we could not hear, and suddenly we build the right kind of ear. Multi-messenger astronomy follows, where one event is studied through light, gravitational waves, and particles, creating a richer, more complete story. By the time you reach the present day, astronomy feels both enormous and intimate. Enormous because the data sets are vast and the collaborations span continents. Intimate because a small signal, a subtle dip in brightness, a faint chirp in an interferometer, can change what we know about the cosmos. And so, our journey for tonight comes to a quiet close. The story lingers, like the last glow of candlelight, as you drift further into rest. If these gentle wanderings bring you peace, I invite you to like and subscribe so that whenever you wish, you may return and we can travel together once more. For now, dear listener, may your dreams be kind and your night be restful. Until next time,